Hello and welcome once again to your favorite YouTube channel, Complanner Studies, where we make difficult things simple, where we seek to explain difficult scientific concepts, difficult mathematical concepts. We make them easy so you can benefit and you can learn out of it. So in this video, we'll be looking at lesson 4, left and right limit part 2 in the Calculus 1 series. We are continuing from the previous video, lesson 3, left and right limits part 1, where we said some basic stuff about left and right limit. We made some lengthy explanations on what a left and right limit is and just the concepts. But in this video, we'll be solving examples, and we're going to be fast about it. We're just going to see different examples, different scenarios in which we can apply our knowledge from the previous video in solving left and right limits in this video. Let's get right into it. So what's our first example for this video? Example 5. Okay, yeah, because the last example we solved was example 4. So in this video, example 5. We've already done this one actually. Yeah, in the last video, the limit of 1 over x as x approaches 0 from the right. We did that in the previous video, and we saw that the answer is infinity, positive infinity. So we can just run through that again. The limit as x approaches 0 from the right of 1 over x. So we know that the answer is going to be infinity, right? We've already seen that in the previous video. And then the other one was negative infinity. The limit as x approaches 0 from the left of 1 over x is negative infinity. As we saw in the graph of this function, as we saw in its graph, where we graph 1 over x, as we saw in the graph, we examined the graph in the previous video, and we saw that our ideas are actually true. So this limit does not exist because by limit, now I'm referring to this limit here. I think we also treated that in the last video. The limit as x approaches 0 now, not from the right or from the left, just 0 as x approaches 0 of 1 over x. This does not exist, DNE, because you are not approaching an exact value as you approach the limits either from the right or from the left. You are not approaching an exact value, so it doesn't exist. We've seen that in the graph here, that it doesn't exist. So we already know that one. So let's look at something more recent. Example 6. The limit of 1 over x squared as x approaches 0 from the right. Okay, this is interesting. The limit as x approaches 0 from the right of 1 over x squared. We'll look at this one. Okay. So this is what we have, and we want to find the value of the limits. So what we simply do is we bring our imagination, we turn our imagination on, and we imagine x approaching 0, right? Values of x approaching 0 from the right. Okay, that's numbers that are bigger than 0. Once we take a look at the number line, you approach 0 from the right, you pass 10, 5, 0.1, 1.62, they are bigger than 0. Okay, and they are positive. That's the basic thing there. These are positive numbers. So let's start simple. What about if we have 1 over 0.1 all squared? 0.1 is close to 1. So 1 over 0.1 all squared is something like 1 over 0.01, yeah, which is 1 over 100. 1 over 100. Now, same thing goes for 1 over 0.001. This is closer to 0 from the right, so get 1 over 0.00000. Yeah, five. You get 5 zeros and then a 1, which is also very large. If you simplify this, you get a very large value. Okay, this one is actually, sorry, this is, sorry, the answer from here is 100, not 1 over 100. 100. What you'll get from here is a million, 1 million, 1 million. So a million from here. Now, we see that the values of f of x have spiked up. We've gotten an increase in the value of f of x. So these are increasing rapidly as we approach 0. So intuitively, you can use this test, but just by intuition. 1 over 0 all squared. 0 all squared would still be 0, so you have 1 over 0, which tends to give you large, very, very large figures. So we can conclude now that the answer to this is infinity. That's the answer to that one. Next example, we see that it's the same question but just different side now. What about the left? What about the left? The limit of 1 over x squared as x approaches 0 from the left hand side. What would we get? Okay, let's tackle that together. So okay, we've got something like this. Limits as x approaches 0 from the left hand side of 1 over x squared. So we are approaching 0 from the left, right? Meaning that we are passing through the negative x-axis. We are approaching 0 from the left. You can just visualize. We've seen this before. You approach 0 from the left. You are using negative numbers, negative numbers to approach 0. So we can, okay, we'll just leave a space here, but let's just do some intuitive testing. This is just like a rough, well, not rough testing, trying to test numbers that are just very close, like minus 0.1 all squared. Now, the thing is, whenever you square a negative number, what do you get? You get a positive number, okay, because negative minus 0.1 all squared is like you saying minus 0.1 multiplied by minus 0.1. And what you get from that is positive, because minus times minus is plus, of course, algebra. So 0.1 times 0.1 is 0.01. So you get positive 0.01 plus, put a plus there, positive 0.01. And we see that this means that we have 1 over 0.01, which is 100. Wow. What if I try minus 0.001 and another number, this time around, closer to 0 from the left? Okay, I'll still end up at 0.000001. That's 5 zeros before the 1. So because the negatives will cancel out. If you're squaring a negative number, you'll get a positive result. There's no two ways about that. So 1 over this gives you a million. Yeah, a million. So we see that essentially when we say when we approach zero from the left, we are still approaching very big positive values. As we approach zero from the, as we put in small negative numbers, we are still getting large, keep on getting larger and larger positive values. So we can now conclude that the limit is infinity. Infinity. So let's use a graph to verify this. 1 divided by x squared, just graph that, and we see something interesting here. As we approach zero from the right, it ramps up at the positive y-axis, goes up. As we approach zero from the left, we are still going up, unlike the graph of 1 over x, that here we were going down, but here we are going up. Just from what we've solved, the graph verifies that. So we go up, we go up. Now, we conclude that the limit as x approaches 0, or for 1 over x squared, either from the right or from the left, is infinity. Therefore, since they both have the same value, as in, this is what I mean. Oh, the graph wasn't the graph wasn't on. Okay, so like this is the graph here. It ramps up at both sides, so that's what I was saying. I didn't turn on the graph, so you guys didn't see that. But this is it. You approach, whether you approach from the left, from the right, or from the left, you approach infinity. You get infinite values. You get infinitely large values. So we basically approach infinity whether we approach from the right or from the left. We are approaching very large positive values, unlike the graph of 1 over x, that this part was going down. You had a dip here. Even from the left, we still have the graph going up. So we can conclude that from our observations on this limit, we see that the limit as x approaches 0 from the left of 1 over x squared is equal to the limit as x approaches 0 from the right of 1 over x squared is equal to infinity. So whether you approach from the left or from the right, you get infinity. Now, although this limit does not exist, hold on, it doesn't exist because infinity is not a definite number. You must have a definite result. Here we don't have a definite result. We have so it doesn't exist because we don't have a definite result. Infinity is not a definite, it's not a real number. You must have a real number result for the limit to actually exist. So yeah, it doesn't exist, but typically we say it's infinity. It's infinity. So yeah, the limit is infinity. So we can actually now say that the limit as x approaches 0 of 1 over x squared is equal to infinity. We could not say anything for 1 over x because we had negative infinity for right side and positive infinity. Positive infinity for right side and negative infinity for left side. But for 1 over x squared, we can actually say yes, okay, it's infinity because yes, both left and right give infinity. So the ultimate result there is infinity. Now we move on to another example. The next one is the limit as x approaches -2 from the left hand side of 1 over x plus 2 all cubed. So the limit as x approaches -2 from the left of 1 over x plus 2 all cubed. So this is what we have, and let's start. So first of all, we look at the function. There's really nothing special about it. I mean, this is x plus 2 all cubed, and you have 1 on top, so there's not much you can cancel. There's really nothing you can cancel here. So our attention turns over to the point, and we are approaching from the left, mind you. We are approaching from the left. So as usual, we picture us approaching 2 minus 2 actually from the left. So we have minus 2, right? Numbers to the left of minus 2 are numbers like minus 3, minus 4 to the left of minus 2 left. Numbers to the left, minus 3, minus 4, and so forth. So if I were to put in minus 3 here, that's how you do it. I mean, just go ahead and put in a test value. See how that's how you do right and left limit. Actually, testing the process of you testing is actually very, very crucial. It's a very crucial skill to learn when dealing with left and right limits. So just put in a test value. What when I put in a number that's to the left of minus 2 in place of x, what do I get? I get 1 over, this is minus 1 all cubed. Now this is minus 1 all cubed when I put in minus 3. So minus 1 all cubed is minus 1, right? Yeah, minus 1 times minus 1 times minus 1 times minus 1. We know that this is going to give you plus 1, right? Minus times minus is plus 1 times 1 is 1. Now multiply by minus 1 again. Minus times plus is minus 1 times 1 is 1. So you get minus 1 when you multiply by the odd. So the thing is that when you have when you have an odd number of negative signs being multiplied by themselves, you get a negative sign as a result. As in, when you have minus 1 to the power of 5, now 5 is an odd number, so you have minus 1 there. Since it's odd, because the last minus would change the plus to minus, so it's just intuitive reasoning there. So we have minus 1 as our answer. When you put in minus 3, we have minus 1. So let's go smaller. What if we put in we're approaching from the left, so we can put in minus 2.1 plus 2. Minus 2.1 is close to minus 2, close to minus 2, but at the left hand side. So if I put in minus 2.1, what do I get? I get 1 over this, and this is minus 0.1. Yeah, minus 0.1, and okay, there's a cubed here. So minus 0.1 all cubed is just minus 0.1. So that's minus 0.001. And this gives me minus 1,000 as my result. Minus 1,000. Now, from what we've seen here, from our previous results, we see that we are getting very, very, should I use the word, we're getting very large negative numbers here. So the thing is that we test, finally we can put in a test here. Let's just put in, like while doing tests here, trying to analyze the function. If I put in minus 2 at where I see x, just a test. So 1 over minus 2 plus 2, or I'm going to get 1 over 0, right? 1 over 0 all cubed, which is equal to 1 over 0. So I'm getting something infinite, okay? But this does not mean that the answer is infinity. This is because I'm using the exact value here, so this is wrong. But this just paints a picture of what we are to expect at minus 2. A very large number is what we're supposed to expect at minus 2. But the thing is, what is the sign of this very large number? Is it a positive very large number, or is it a negative very large number? So the final analysis we're going to do is that we know that for x plus 2, okay, for x plus 2, if we use any number that is that's less than minus 2, as in let x be less than minus 2 now, okay, if x is less than minus 2, then what's x plus 2? What can we say about the sign of the sign attached to x plus 2? So you try numbers like minus 3, you get minus 1, minus 0.1, you get minus 2.1, you get minus 0.1. So you always get a negative number, negative, because the numbers you are using are less than minus 2. Okay, they are less than minus 2. As in, you can have minus 100 plus 2, which is minus 98. So they will always be negative. Now, using that, okay, let's copy. Using that, this can actually happen very fast. It's not this. I'm taking this long because I want you to understand the way I think, the way I reason, the way you can just reason. It's a very fast reasoning process. Once you just get the hang of it, it just becomes very fast and easy. It's just that I'm trying to teach you this process of you being able to reason out a limit. So you're getting a negative sign. So your answer here is negative something all cubed. Now that something you are choosing is approaching minus 2. So it's approaching minus 2, and at minus 2 the denominator is 0, and minus 2 it's 0. So that means that the closer you get to minus 2, the closer the denominator gets to 0. The closer you get to minus 2, the closer the denominator gets to 0. We saw this happen actually over here, where we used minus 2.1, which was close to minus 2. At the denominator, we got a number that's close to 0 but had a negative sign. So it gives us a picture here. So we had minus 0.1 at the denominator. So what do you expect? The cube here will not affect the negative sign because it's a cube. If it was a square, the negative sign would change to positive. If it was to the power of 4, it will change to positive. If it was to the power of 6, positive, 8, 10, a million, positive. But if it's an odd number powers like 3, 5, 7, 9, 11, it won't affect the minus sign. The minus sign will still be there. So you have 1 over minus something all cubed. Now that something is essentially 0 all cubed. That's something actually. It's essentially, it can be approximated as 0 because you get minus 0.0001. So essentially 0. So you can see where this is going. We're getting to minus infinity here. Minus infinity. That's where we are actually headed. That's where we're getting. So the answer to this problem here is the answer to this limit is minus infinity, because we approach very, very large negative values. You can verify this on a graph. So we just go ahead and punch in 1 over x plus 2 all cube, and we get it. So we're looking at minus 2, right? Now if you look at minus 2, as I approach that minus 2 from the left, you can see the dip to negative infinity. That dip goes on forever. It will never reach the line x is equal to 2, it will never reach the line x is equal to 2. It's never going to reach that line. It's just going to keep on going like that and like that and like that and like that. So the line x is equal to 2 is a vertical asymptote for this graph. We'll cover vertical asymptotes soon. Now, we've answered that question, and we can move on to our next problem that tells us to evaluate. Okay, we're done with this part. So example 9 says, what's the limit of tan x as x approaches pi over 2 from the left? Now, two new things we are seeing here: a trigonometric function for the first time and this pi over 2. What does this mean? Okay, I'm going to be explaining that. So first of all, let me just write that down. Tan x. So we look at what we have, and we have this limit, right? We are approaching pi over 2 from the left. So usually when we work with trigonometric functions, I believe you know what trigonometric functions are beforehand. I don't want to go into details of trigonometric functions now, because that's not what this may be. I might produce another video on trigonometric functions. For those of you that don't understand, you can just put your thoughts in the comment section if that video should come out about trigonometric functions. There are some things you need to know before you step into calculus, right? Like what is tan x, sine x, cos x. Those are basic stuff. What we're handling in this video is limits. So pi over 2, as we all know, it's in radians. This is just in radians. Pi over 2 is 90. It's 90 degrees. This is in radians, actually. Again, I don't really have time to cover what radians are and all that. We are focusing on limits in this video. So 90 degrees. It helps you when you understand the graph of tan x in this. So of course you need some training beforehand. But let's see here. When I graph tan x, the shape of tan x is very popular. So pi over 2 is like 1.59, I think. 1.59 something. Okay, but okay, for the sake of easy readability, let's use degrees. Let's make use of degrees. Just so the x-axis is in degrees. So at 90 degrees, pi over 2 in radians is 90 degrees. So can we spot 90 from here? Yes, we can. So we are approaching 90 degrees from the left, and as we approach that 90 degrees, we see that we ramp up. And we never really reach 90 degrees. We keep on getting high values, like okay, at 88.99 degrees, that's close to 90. You're getting 50, okay, 89.01, 57.86. It just goes on like that. So you'll get high and higher values of f of x. So the limit is positive infinity, as we can see clearly. This is pi over 2. This is in degrees. So we've seen the limit from there. So we can conclude that the answer to this is positive infinity. If we were to approach it from the other side, that's from the right hand side, if we try approaching from the right, this is the right, so we get a dip to negative infinity. Maybe from the right it's negative infinity. There's really no solving here. You just have to know how the tan graph is shaped. Like, there's really not much of solving. There are questions like that. We have to know how a graph is shaped, like trigonometric functions. Would teach you more on that. So back to business. We are looking at example 10, which tells us to evaluate this limit as we approach 7 from the left hand side. So the limit of absolute value of x squared minus 4x minus 21 divided by x minus 7 as x approaches 7 from the left. Evaluate this limit. So I'm just going to write that down. Limit as x approaches 7 from the left. Absolute value of x squared minus 4x minus 21 divided by x minus 7. All right. So this is what we have to work with, and we look at the absolute value. The absolute value is on the numerator here. Now notice also that 7 makes the denominator 0. 7 makes the denominator here 0. So you'll be coming across functions like this very often, where the denominator is being made 0, the numerator has an absolute value function. You have some special properties once you do that. But our quest here is to solve the problem. So let's just do that very quickly. The first thing we want to do is that we want to simplify the numerator. Since it's a quadratic equation, let's simplify it in hopes that something can cancel out. So to factorize, okay, for those of us that don't really know how to factorize quadratic equations, I guess I'll do that step by step. I won't really dwell too much on this. Just take 21 and multiply by the coefficient of x squared here, which is 1 actually. The coefficient there is 1, so we have minus 21. When you do minus 21 multiplied by 1, minus 21. We then go on to list the factors of 21. Let's start with factors of 21. We have 1 okay, factors. Okay, let's just list the factors. 1, yeah, 3 can go 7 times. 4 can't go, 5 can't go, 6 can, 7 can, 8, 9, 10, 11, 12, 13, 14. I'm not seeing anything that can actually give us 21 again, apart from 21 itself. So these are the factors. Next, you find the pairs that multiply to give 21, like 1 and 21 multiply to give 21, right? 3 and 7 multiply to give 21. Okay, 3 and 7. Next step is to look at the sign here. It's negative. So either the thing is that one of them is going to carry a positive sign and the other one will carry a negative sign. So we can say, okay, we have 2 alternatives for each pair. First alternative is minus 1 and 21. Next is 1 and minus 21. Next alternative is minus 3 and 7, and then we have 3 and minus 7. When you multiply these two numbers together, you will get minus 21 in either case. When you multiply minus 1 and 21, you get minus 21. So that's just the basic idea there. When you multiply the two of them, you must get minus 21. Then you look for the 2 pairs of numbers that when you add them together, it gives you the number you have here at the middle, which is minus 4. So of course, I can turn to either minus 3 and 7 or 3 and minus 7, because those are the minus 1 and 21. 1 and 21 can't give you 4. Either, however you mix the signs together, you can't get a 4 out of 1 and 21. But 3 and 7, you can actually get a 4, because 7 minus 3 is 4. So minus 3 plus 7 is 4. But we're looking for minus 4 here, not 4. Minus 4. Minus 4, not 4. So 3 minus 7 is minus 4. So I'm going with these. So our factors are 3x and minus 7x. 3x and minus 7x. So replace 4x minus 4x minus 3x with plus 3x, because it's 3x and minus 7x. So minus 4x is being replaced with plus 3x and minus 7x and minus 3. If you notice, these two plus 3x minus 7x give you minus 4x. So next you pair them together, and you factorize each pair. I'm not going to go into too much detail. This isn't really part of x into x plus 3. X is common between x squared and plus 3x. X into x plus 3. Then minus 7 into x plus 3. Yeah, minus 7 is common. Minus 7 into x plus 3. And we end up with x minus 7, x plus 3. So you just pair the first two here, and pick one of the brackets. So this is what we have. Now we can now use this to solve. This is the limit. At the numerator, we go ahead and replace what we have here with what we have here. They're the same thing, but just this is the factorized version. Notice the appearance of the x minus 7 there. X minus 7, x minus 7, x plus 3. We have x minus 7 at the denominator also, but it's with no absolute value. We can move on, further simplifying this to, as we did in the previous video, breaking this down to absolute value of x minus 7 multiplied by absolute value of x plus 3 divided by x minus 7. Broken it down to absolute value of x minus 7 multiplied by absolute value of x plus 3 divided by x minus 7. Then the sign, we also have to consider the signs here. The signs. Now, I'm approaching 7 from the left, meaning that I'm using numbers that are less than 7, right? So we consider x minus 7. Okay, so 6 minus 7 is minus 1, right? Any number that is less than 7, that you subtract 7 from it, you get a negative number. So of course the result from here, the result you get out of here is going to be negative. As you approach from the left, it's going to be negative. You're using numbers that are less than 7 and subtracting 7 from them, you're going to have a negative number. Now, in here too, it's negative, but the absolute value turns into positive, as we had already covered this in the previous video, so we're not going to dwell too much on it. Let's just walk through that. You can see the previous video, lesson 3, left and right limits part 1, for more details. So on top is positive. We have an x minus 7 there on top, and multiplied by absolute value of x plus 3 divided by negative x minus 7. The negative here just indicates that both of them have different signs. So when you cancel them out, you get a negative. Plus divided by minus is still the same thing as minus divided by plus. They have different signs. They have different signs. Negative. So you have a negative coming out of as a result of the two of them having different signs. The absolute value here turns the negative to positive. Turns the negative to positive. But the denominator maintains this negative sign. So this will cancel this. you're left with limits as x approaches 7 from the left of, well, this divided by minus 1 is minus that, so you have minus plus 3, and yeah, as usual, the constants can come out from the limit. So minus 1 multiplied by limit as x approaches 7 from the left of absolute value of x plus 3, and our result is we just put in 7 here, and we get minus 1 multiplied by absolute value of 7 plus 3, which is equal to minus 1 multiplied by absolute value of 10, which is equal to minus 1 multiplied by absolute value of 10, which is equal to minus 10. And that's our answer for this one, minus 10. So yeah, we are done with that. And let's move on to the last example, since we are already, this video is already taking a lot of time. In the last example, we have the same thing, but just from the right, right? Yeah, the same thing, but from the right. You just follow through the same steps that we did, the same steps, but just that when you get here, okay, I don't really need to write that much, so just a little bit of explanation. Once you get here, you won't have different signs anymore. Why? Because you're using numbers that are greater than 7 this time around. As in, you are approaching 7 from the, you have limit as x approaches 7 from the right of absolute value of x minus 7 multiplied by absolute value of x plus 3 divided by x minus 7. That's what you have when you simplify. So you're approaching from the right, meaning that you're using numbers like 8, 9, 7.1. By the way, 7.1 minus 7 is 0.1. 7.1 is greater than 7. You're approaching from the right. Number is greater than 7. So 0.1. This is positive. So this will be positive. And the absolute value function, well, it would a positive number will still remain a positive number with absolute value function. So they can basically knock off. Because without attaching a negative sign, they can easily knock each other out. So yeah, you end up having something like this, where this can knock off this, and of course, putting 7 where you see x here gives you absolute value of 7 plus 3, which gives you 10. So on the when we approach from the left, we had minus 10. We had minus 10 approaching from the left, but now we have a 10 approaching from the right. So just about you picturing it, knowing what you're doing, knowing how you approach the specified value, knowing that okay, I'm using numbers that are less than that number there. So okay, I'll have a negative sign, I'll have a positive sign. That kind of intuitive reasoning will get you through left and right limits. So to crown the video, let's just see a graph of that function, just to wrap as we wrap the video up. So function is absolute value of x squared minus 4x minus 21, okay, divided by x minus 7. Yeah, so graphing that, and we can clearly see the same gap here. that we saw in the previous video. So of course we know that the limit does not exist. The exact limit at x is equal to 7, that's not left or right this time around, but the limit at x is equal to 7 does as x approaches 7 from the left or from the right does not exist, because I'm approaching negative 10 as I approach from the left, and I'm approaching positive 10 as I approach from the right. Okay, we're not seeing 7. Okay, so there's 7 there, and 7, 8. So we see that as we approach 7, as we are approaching 7 from the right hand side, approaching 10, as we are approaching 7 from the left hand side, this is 7 here, from the left hand side are approaching 0.99999 gives minus 10. So the limit does not exist. So that's all you need to know about left and right limits. That brings us to the end of this video. If you have enjoyed what you have seen, don't forget to like the video, subscribe to our channel, share the link with your friends who are struggling with this subject, this course, Calculus 1. That will be all for this video. I'll see you in the next video.